What time is it? It's science time.
Oh, it's science time. Let's all stop and just unwind. 1, 2, 3, 4, here we go. Learn so much your brain explodes. Lessons so cool, so fresh. Beat so big you'll lose your breath. Learning facts and real cool stuff. Scream for more, keep getting up. It's science time. It's fun, you best believe. Explore and learn new things. Come and join me, please.
I'm Mr. C, and this super smart group is my science crew. Working together with my crew makes learning so much fun. Actually, you should join us. Let's give science a try with a simple DIY.
Today, we're learning about the McWane Science Center. What time is it? It's science time.
Welcome back to DIY Science Time. My name's Mr. C, and I'm so excited to have you here with me as part of my science crew today. We're at the McWane Science Center in Birmingham, Alabama, and we're going to explore this amazing DIY facility. It's going to be electrifying, and we have some shocking things that you're going to learn with me here today. Are you ready?
Experts agree it's very important to have a balanced diet. Today, let's create balancing sculptures. To get started, you're going to want to gather some materials. You'll need a tall water bottle, scissors, tape, skewers, chenille stems, or any other fun and balanceable materials you might find. And don't forget, hungry scientists should always have their scrumptious science notebook.
A science notebook is a tool that every scientist should have because it gives us a place to record all of our learning. Taking notes and being organized allows us to be better scientists. A science notebook allows us to go back and review all of the data and information we've gathered during our experiments. Plus, it allows us to share results with other scientists who might be interested in learning more about what we've discovered. Whenever you see the notebook pop up on the screen, like this, it's a reminder that this is a good place for us to jot down new information during the show. I've already added a title and the list of materials for today's activity. But our crew is still going to have lots of information to collect and organize as we go through our experiments. Most importantly, the more you use a science notebook, the better you'll get at taking notes and recording data. If you don't have a science notebook already, download a copy of Mr. C's science notebook from the website.
So I'm here with Rachel, an educational specialist at McWane, and we are going to talk about nails and balloons?
Yes, we're going to learn about pressure with our nails and balloons today. So what do you see in front of us right here?
Lots of nails, a bed of nails, so to speak.
That's right. What do you think is going to happen if we touch a balloon to one of those nails?
I don't know, we should try just to make sure.
Let's try it out.
All right, got that blown up.
All right, we've got a couple of nails right there.
All right. All right, they are sharp. They are sharp.
Pretty sharp. We pretty much expected that was going to happen. Do you think we're going to get the same result by touching the balloon to all 100 of these nails?
I don't know. I think we should find out.
Let's try it out.
You would think that it's going to do the same thing, right?
Right, you'd think so, because those nails are extra sharp.
All right, so
go ahead and put that balloon on this bed of nails.
All right.
And we're going to add some more pressure right here. You ready?
Yes.
All right, are you plugging your ears?
Should I?
I don't know. We'll find out.
Oh, yeah, if it pops that loud. I'm going to let you push this.
Okay, we'll push it down a little bit.
Oh, you're backing up quite a bit. Come on. Oh, whoa.
I'm pushing down pretty hard right there, huh? But that balloon is not popping because of all those nails. So when we popped the balloon with that one nail, it's a lot of pressure in one point on one point of the balloon. But when we put our balloon on this bed of nails, it's spread out that pressure over all of those points. So it's taking that weight and it's spreading it out over an area.
I mean, it would be awesome if there was something bigger than that.
Well, you're in luck. We do have something bigger than that. Do you think you would want to be this balloon and be on a bed of nails?
I'm a lot heavier than that balloon, so I'm not sure if I will pop or not.
All right, well, let's try it out.
Okay.
All right, so here's our bed of nails. Go ahead and lie all the way down for me.
Should I grab this?
Yeah, if you want to grab that, that's our button that's going to raise up all 1,000 of those nails. All right, so whenever you're ready and you're feeling brave, go ahead and push that button.
3, 2, 1. Oh,
There we go. All right.
That is awesome.
What does it feel like?
Really like nothing.
Yeah, so even though you're lying on thousands of nails, your weight is spread out over an area, just like we did with our balloon experiment. So it's not pointing into you.
I didn't pop. Nice. That is so cool. It has a weird sensation.
Mm-hmm.
Oh man, I think kids just should come out and try this sometime if they can. This is so cool.
Absolutely, yeah.
There's so much science to explore in your home, but sometimes it's wonderful to be able to visit a science center. McWane Science Center in Birmingham, Alabama is a fantastic place for curious kids and families to visit. Each floor of the Science Center is dedicated to amazing science concepts, which allow for engaging educational adventures. If you're into dinosaurs, light, or anything science, McWane has your science crew covered.
Did you know that dinosaur skeletons you see on display at museums aren't actual dinosaur fossils? They're replicas. Replicas are identical copies created using a cast or mold. If a fossil is too delicate, other methods, like 3D printing, can help successfully recreate these creatures for display. Replicas are important because they help preserve the original fossils and keep them safely available for further study. Those are some pretty awesome knockoffs.
Rachel, what are you doing? You have me strapped in this awesome thing. What's going on here?
Yes, you're strapped into the high cycle. So this is a bike that's going to pedal out 2 stories over open space.
Okay.
So this is like a normal bike, except we've got a large counterweight below it. So that counterweight weighs 250 pounds. Just like if you were on a seesaw with an elephant, the elephant is always going to be on the ground, right? So this is like our vertical seesaw. You're going to be keeping your center of gravity stable, even if you rock side to side. Are you ready to try it out?
Absolutely. This is
All
going to be
right.
awesome.
Excellent. So I'm going to raise this lever, and you're going to pedal backwards just like a bike on the count of 1, 2, 3.
Oh, that's... Oh.
There we go.
I can feel a wobble.
Yeah, it wobbles a little bit. That's right, because it's not being held onto that rope. It's just the science of that counterweight that's keeping you upright. Do you want to try rocking it side to side?
Sure. Oh, that's... Whoa. That's awesome. So I can feel myself like being able to counter the weight.
That's right, yeah. Even as that counterweight is tilting, your center of gravity is changing with it.
All right, that's as... Yeah, I'm not gonna rock it too... Whoa. Yeah, that's so cool. So I'm gonna pedal backwards. I'm noticing it's starting to get like harder to pedal.
That's right, so this rope is using a lot of tension, and it kind of makes a shallow U shape. So as you pedal past the middle, it's almost like you're pedaling shallowly uphill.
Oh,
So
yeah.
when you notice, yeah,
Now
it's
it's
gonna
super
be
easy.
easier, yeah. And then it'll start to get a little harder as you come all the way back in, go nice and slow, all the way until you hear that click. There we go. All right, leave your feet up on the pedals for me, and I'm gonna close up that lever. How was that?
That's
That was
amazing.
awesome,
It's
right?
so cool when you can like swing back and forth
Yeah, that's
and feel
right.
confident you're not gonna fall anywhere because that counterbalance is definitely heavier than me, and it just keeps me kind of like, my center of gravity's down low.
Exactly.
Oh, that's awesome. We are building our very own balanced sculptures today because the high cycle inspired me to try this. It was so cool to be up on that high cycle, just waving and balancing and trying to figure things out. It was so nerve-wracking, but science kept me in my seat and kept me from tipping over. And we're gonna use science today to build a balancing sculpture that'll behave similarly. Are you ready to give it a try?
Are you ready to give it a try?
So here's the thing. This carrot right here won't balance itself. We're gonna use weights and counterweights to get it to balance. And I have a smaller version here that I cut down so that I can keep it in frame and so that we can see everything that we're building. And also what I learned is that all of the counterweight was down low. I'm gonna start with trying to get my carrot to balance on its own by just getting these skewer sticks set in here. Add some weights to give it some mass. I think my carrot needs some hair. I'm gonna turn him here for a second. Whoa! Oh my gosh, it's working. It's totally balanced. Everything is perfectly aligned. The carrot is super happy. He's hanging out. Look at that. Give it a try. Get to the root of creating a balanced system at your house with things that you have lying around.
The test Tesla coil was designed by Nikola Tesla in 1891. It is a type of electrical transformer that can transmit electricity wirelessly. Electricity is stored and built up in the coils of the device before it releases a spark of electricity that shoots through the air. McWane's Tesla coil can produce well over 1 million volts of electricity. Now that's some shocking science.
Career connections.
I am super excited because I am with June Everol of McWane Science Center, and he is a paleontologist who focuses on sharks. And June, I'm looking around the room and I am covered and surrounded by sharks. It's a little intimidating, but tell me what it is you do and what you get to study.
Yeah, so I am actually in the research side of McWane Science Center. I know many people have seen our exhibits, our paleontology exhibits with dinosaurs and such. Well, if you look behind the glass, you will see me. So I actually am a shark paleontologist where I study fossil sharks. And a lot of people don't realize that we are hands down the best state in the United States for fossil shark teeth.
Why do we have so many shark's teeth here specifically?
Alabama is very unique for a lot of reasons, but mainly we're very unique geologically, where we have more geologic time periods laying on the surface of Alabama than any other state. We are the #1 state for what's called paleobiodiversity, and that's just the fancy way of saying different species of fossils.
So fossil shark teeth, I'm looking here, I see jaws, which are cartilage, and I see lots of teeth. Is there anything specific that you studied that is like your favorite type of shark?
Yes. So obviously I like big sharks. So not only big sharks on the fossil record, but I like big sharks that we can find still in the Gulf of Mexico today. So I actually do both. All paleontologists have to study the recent world to understand the past. So for me to study fossil sharks, I have to understand recent sharks like the ones we have here.
So are these here recent?
Yes. So what you're seeing here is a great white shark jaw.
Okay.
All right, so great white sharks have some of these most simple teeth where they're essentially big triangles. But what I study is that depending on where you are in a shark jaw, the teeth are going to be shaped slightly different. It's called heterodonty. The biggest teeth are generally in the middle. These are the ones that are doing most of the business. But they get smaller once you get towards the jaw hinge down here, so they can close their mouths.
Okay, that makes sense. That's really cool. Now, here on the table, I noticed something ginormous. That's a big tooth. And I'm looking at it, but I noticed it looks similar to this guy.
You are very much right. So this is a tooth from Megalodon, the largest shark that ever lived.
That's a real tooth?
This is a real tooth. This is about 20 million years old. And then Megalodon, about the size of a school bus. All right, so by far one of the largest predators to ever live. They went extinct about 3 million years ago.
So they're extinct. So how do we know what they look like, what they did, and those types of things?
Yeah, so that's one of the big parts of paleontology where it's another thing where we have to look for what's called a modern analog. Some shark that's living today that looks very similar to this.
Ah, I gotcha.
Aha. So you noticed how similar these triangular teeth are. These are very similar, big triangles with serrated edges. Now, what's interesting is these are two completely unrelated sharks.
Correct.
So they're within the same order of sharks, but they're completely different shark families. But since sharks their teeth are specially adapted for their diet, these two sharks just happen to evolve similar shaped teeth because they have very similar diets. We know that this shape type tooth here is perfect for eating a blubber-rich diet or eating marine mammals, maybe things with a lot of fat. When you look at great white sharks, they're eating seals and things like that, and Megalodon, very similar. Probably eating manatees, whales, those types of things. It's just the perfect tooth design for that.
So we get a sample here to the space. What does going through a sample look like to excavate teeth, bones, cartilage? Like how does that happen here?
We build what's called a field jacket. It's the same technique that's been used for a couple hundred years in paleontology where we bring back that entire chunk of earth. So would you like to see a field jacket? I've got a nice one in the lab I can show you.
I think that'd be amazing.
Follow me.
All right.
Here is an example of a field jacket. Right? So this is how we recover larger specimens that we find out in the field. This is a 4.5-foot skull of a mosasaur. It's kind of like a large swimming monitor lizard that was laying all over the ground. And so when we find something, a little bone sticking out or so forth, we uncover to see if there's more bones. And if there are more bones, we keep on uncovering and uncovering on the surface to see how much is there. It takes too much time out in the field, and these bones are too fragile to separate the bone from the rock out in the field, so we build what's called a field jacket, meaning once we know how much of the specimen is laying on the surface, we start trenching around it.
So the perimeter.
Yes, yes. So it's building almost like a pedestal where the fossils are sitting on top of this rock mound. We then take burlap and plaster, so there's burlap strips and plaster you can buy at the hardware store, and we build this giant protective casing to bring back that entire chunk of earth to the lab. Now, the interesting thing you're seeing here is that this is almost done with what we call fossil preparation. That's where we have specialized tools here in the lab to separate the bone from the rock.
Okay.
But what you're seeing here is actually upside down.
I was going to ask that.
Yes, so when we do a field jacket and we cover the top side, the top of the skeleton is already uncovered. But if you just started pulling the bones out right there, you would tear them in half and destroy the specimen. So we actually build the field jacket, flip it over,
And then sort of lift.
and this is the bottom side. So the part we were walking on is here at the bottom. But now we're taking all the rock off from the backside. So we're almost done here. So you can see right here is part of the lower jaw. You can see some of the teeth coming out. And you can see right here, this animal died upside down. This is the very, very top of the head. It's a bone called the frontal. So here is part of the bone, the jawbone that we got out already.
That's amazing.
And so you can see, and this is only half of the lower jaw
and that's
from this
going to
animal.
flip right here onto that part.
Correct, yeah. So this was actually in a different part over here that we got out already. So this is one half of the jaw. The other half, the mirror image, is still in the rock.
That is, and how old is this creature?
This particular specimen here is about 82 million years old.
That's amazing.
Yeah, found in Dallas County, Alabama. These teeth here are gigantic things. This is the top predator at the time. This is called a Tylosaurus, which is a type of mosasaur. So really big swimming monitor lizards that really ate anything they can put in his mouth.
This has given me and our crew at home something to sink our teeth into. And we've really been able to hopefully inspire kids to want to get out, dig, and learn about really what's underground under their feet.
Absolutely.
Super cool. Thank you so much. Appreciate it.
We've unearthed a lot of fun at McWane Science Center so far. Mr. C threw his weight around on a high wire cycle and also had a chance to build his own balanced sculpture. I'm confident you can create an even more beautiful balancing sculpture. And we met a paleontologist and learned how fossils can show us the history of the world. Roar!
We are at the McWane Science Center at the Rushton Theater, and I'm here with Chris, who's an educational specialist, and today we're going to be doing some combustible science.
That's right. You see, combustion. What do you know about combustion?
We need fuel, heat, and oxygen for combustion.
All right, now propane is invisible, just like your CO2, but this bubble solution lets us make the invisible visible. There it goes.
So we have our fuel.
That's right.
We have oxygen.
Where's that heat gonna come from?
Ta-da.
3, 2, 1, and yeah.
Oh, that's awesome. What a beautiful flame.
Fuel, heat, oxygen, combustion.
There we go. I think that might be just about enough. I'm gonna get my scoop. There we go. And you've got your lighter, I've got mine. Here we go. 3, 2,
1. That's awesome.
Fuel, heat, oxygen, combustion.
All right, we have a balloon here. It looks like a birthday balloon. I'm super excited. We're celebrating combustion. What's
Yeah.
inside this balloon specifically?
This is no birthday balloon, because that is not helium.
Ooh.
It's another very light gas, hydrogen.
Oh, okay. Yeah, also floats.
Also floats, but it doesn't just float.
It blows up.
It blows up.
In the bottom of my balloon is iron, which, if I do this right, will give us a nice, beautiful rain of sparkles.
Well, let's give it a try.
Let's give it a
So
try.
we have our goggles, we have our lab coats. This time we're actually gonna put on some earphones
That's right.
because we want to protect our hearing, just in case that it's loud. I can still hear you a little bit. Can you hear me? Perfect. All right, here we go.
All right. In
3, 2, 1. Wow!
Wow.
Wow!
Wow. Yeah. Happy birthday, huh?
Oh my gosh. That was so cool. Fuel, heat, oxygen, combustion. That was amazing. I wonder, do we have other balloons that we could do some other colors with?
I got you covered.
3, 2, 1. Whoa! Oh my gosh. Whoa! Fuel, heat, oxygen, combustion. That was awesome. Today was amazing, Chris. I really appreciate you taking the time to hang out with me, to illustrate and explain combustion. And I just had a whole bunch of fun learning. And I know our crew at home is also going to be able to enjoy watching this and learning from all these demonstrations that we did. So thank you so much. Really appreciate it. And to many more science experiments together in the future.
Welcome back anytime.
All right. Thank you so much.
Did you know there is a fourth state of matter? Plasma. Plasma is an electrically charged gas. A plasma ball is filled with low reacting gases and has a high voltage electrode at its center. When electricity is sent through the conductor at the center, plasma stretches from the electrode to the glass, creating beautiful beams of colored light. When you place your hand near the glass, the charged beams of plasma are attracted to your hand. Now you're a conductor too. That's some energizing science.
There's so much to add to our notes today from the McWane Science Center. Mr. C and Chris exploring combustion? That certainly was explosive. Can you think of any other machines that use combustion? I'm adding a special note to remind us all that we should never play with fire or do experiments like that at home. Let's leave that to the professionals, like Mr. C and Chris. I've also added photos of the plasma globe. Plasma perfection.
The bed of nails. Can we repeat it at home? I think so. We want to create an array of thumbtacks, which means we're going to try to space them out evenly. I'm going to try like an 8x8 or a 10x10. It just depends on how many I can fit here in the center of this aluminum pan. So, are you ready? Let's get to it. So I'm using the foam underneath so that I can push the push pins right into it without having to worry about pushing into the table, just to protect the furniture. I'm trying to make sure that I'm pushing them straight down so that when I flip it over, all of the push pins will be vertical. I tape this across the bottom just like this so that these stay in place when I flip it over. All right, now we flip it over. All right, so I'm gonna lift one of these up at a time. Ooh, look at that. Gotta be really careful, I don't wanna bend these out. Oh my gosh, that looks perfect. There are a couple that missed the foam, but that's okay. I think I'm gonna leave it like this so that you can see all of the nails against the white backing. And then, well, not nails, but you know, push pins. So now we're going to blow up a balloon. All right. I'm a little nervous. We're gonna set this on here. Okay, it hasn't popped yet. And then I have my other pie pan, which matches this pie pan, and I have some extra cardboard in here because I'm gonna apply pressure, and this is gonna help protect my fingers in case the balloon pops. All right, so here we go. Woo! Oh my gosh. All right, I got a little bit of pressure on it, but I was pushing really hard. Let's do another one. It also could be a situation where my pins might not be lined up properly, so one pin was applying more pressure than another pin. All right, here we go. Are you ready, little blue balloon? You can do it. You can do it. All right, here we go. I might also need more nails or pins. Look at that. It works. That was awesome. It works. Well, the green one didn't work. The blue one did work. Give it a try. build your own bed of pushpin nails and see if you can keep your balloon from popping. And just to prove it actually will pop, it does. And if you haven't done so yet, make sure you hop online and download your DIY science notebook. That's right, your notebook is a great place to put information, to keep track of your experiments, and most importantly, have a place to come back to see what happened in a previous experiment. What an amazing day. McWane Science Center is so much fun, you have to check it out. High cycle, bed of nails, combustion, all sorts of amazing things, and the fossils, awesomeness. That's right, it was so cool. Keep learning, keep exploring, keep having fun, and remember, science is wherever you are. All right, little green balloon, we're gonna give it one more try. You can do it.
It's science time. It's science time.
It works!
It's science time.
Good catch. What happens when you pop a balloon? It pops.
It's science time. It's so much fun. Learning fun for everyone.
Wow, that's dangerous. Oh, I'm sliced up. Beautiful. That was. What day is it? It's science time. Whoa. That was awesome.